Alright, decided to do a part 3, so I just want to modify um, what I'm proposing is a possible explanation that doesn't involve any wave theory for the diffraction pattern. What do they call it? Refraction, or it's probably got to be a better word for when an electron emits something. So I did come up with a phrase like electron lensing effect. You know, it's sort of dependent on what the electrons are doing will decide what the photons will do. And in any one of these circumstances, essentially the electrons are behaving like a lens and changing where the photon goes. But anyway. So I guess we'll do the idiot's comment first. The McCool guy deleted his comment, but I left it here just just to respond to it simultaneously. So I say that word in perpetually, so you can't say perpetual. That's some more. You really sound educated. So if you don't pronounce words exactly how they're supposed to be pronounced, you're uneducated. I constantly play with words, so yeah, that's just my personality. Sorry, but I've always done it, and I always will. So fucky Yui. I mean, you don't even understand the fucking basics here, whatever that means, right? I don't think you understand the fucking basics here. If I poke a puddle of water with my finger, the waves that radiate will not interfere with themselves. Retard. Or rather, you want so badly for light not to be a wave as it doesn't fit with your theory. Well, again, we've been over this before. I didn't have any theory before I stated the whole concept of a wave never, ever, 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 ever in my lifetime made any sense. Because I didn't pay any attention to it in grammar school science. As soon as they said electromagnetic spectrum, I said, oh, you mean those photony things. Yeah, I never waved them ever because it never made any sense, and it never will make any sense because the whole concept of calling some discrete thing a wave doesn't make any sense. Waves propagate. All right. And if they don't, if you have a standing wave, then you have to have a medium, retard. That you contrive any number of excuses to throw out evidence. Now, I'm not throwing out evidence, I'm explaining how the evidence is weak. Now, your obligation is to show how it's strong evidence. Now, I'm saying the similarity between water waves in the single slit and light in the single slit is non-existent. There is no similarity. I call that a flaw in your wave theory. Now explain how it isn't a flaw. Twist facts. No, you're the one twisting them. And I'll show the page he links to is the Wikipedia page on diffraction, which is nothing but a perverse twist. They bring up Huygens' principle. The principle they don't apply in the double slit experiment. So Huygens happens in the single slit, but Huygens doesn't happen in the double slit. That's a physics principle. You use something, a principle, in one circumstance only, and don't apply it to anywhere else in the universe, because guess what? It doesn't work. Oh, that's physics. That's being scientific. Selective use of principles is being a scientist. So you're the one throwing out Huygens when it's to your advantage. Oh, well, it'll screw up the two-slit experiment if I pretend Huygens exists. It'll make it the four-slit experiment. So I can't use Huygens because it won't work. To make it so it's in your mind. Well, again, I can only show how that's exactly what you're doing. You're saying it's acceptable to apply a principle in one circumstance to make something work and not apply it anywhere else because it will break the rest of the physics. And you're saying that's not twisting it to satisfy your mind. Let's tell me acknowledge the evidence that supports my theory. Well, it sort of makes sense to do that in some respects, but again, I'm obviously acknowledging this other counter evidence and pointing out how it's not correct. So I am acknowledging it. What you're saying, I have to acknowledge not the evidence, but their conclusions drawn based on the evidence. I'm saying the evidence exists. You're the one pretending there's single slit wave diffraction in water. You're the one pretending there is, not me. You're saying it's a fact when it's not. And then you're drawing a conclusion that you're saying I must agree with. You say the photon has to go through both slits. That's your conclusion. You have no evidence that it went through both slits. It's your conclusion. And I'm explaining how your evidence that's making you draw that conclusion is it does not necessarily have, it has explanation by other mechanisms. You're not dependent on photons going through two slits. And quite obviously in the single slit diffraction, it doesn't go through two slits. It goes through one. And throw everything else out. Great science, buddy. Well, look, dude. Yeah, you're the one who's clueless. I can only keep pointing it out. You can keep evading the subject, which you keep doing, or changing the subject, which you keep doing. So, what else can I say? Show me somebody poking a puddle and creating interference patterns. Show it. And then I'll concede it exists. Until you show it, fuck a Yui. Even molecules have been shown to have wave-particle duality. Well, see, again, that's your conclusion. Wave-particle duality is your conclusion based on the evidence. You're saying that there's some proof that charged bodies, moving past charged bodies, diffract. Well, yes, I agree, they do. Charged bodies will diffract. They'll do that. So if you can put enough charge on something to equal its mass, you could probably do it with cannonballs. So if you took magnetic cannonballs and threw them through a magnetic slit, I'm sure you can get the cannonball to move in terms of its momentum. It won't tomato on the wall. The cannonball will diffract. Yeah, because you've created a force parallel that somehow is somewhere similar to the one on the atomic scale. But you're the ones that keep pretending there's no such thing as a nuclear scale, that atoms and molecules and the structure of matter is some kind of solid thing, that there's no atoms in the matter. The matter isn't made of atomic nuclei and structure. You're the one pretending that's the truth, and that's not the truth, idiot. Retard. Fuckface. Do you understand that, retard? Do some reading. You clearly haven't. Well, clearly I have watched a lot more lectures than you have, asshole. And I'm certainly seen the two-slit experiment done many hundreds of times, more times than you. Hundreds of times, more times than you. Like you, it's 4 to my 400, asshole. Alright, so then he links to the Wikipedia page. Let's do the Wikipedia page quickly. Just horrible. So it starts off with Newton's rings, which, again, it's light. And clearly the interference you can see out here in the periphery. So that's the same thing as the single slit experiment. You just cut the top off. Just kick a band in here, and then you'll see that the little dead spots show up. Obviously they didn't do this plainly, because that's why you end up with a spiral, so I don't know exactly what they did to create that. Another light effect here. This is Young's drawing of the two-slit experiment. It's a drawing of, yes, what happens with the two-slit experiment, which isn't diffraction. That's supposed to be an interference pattern. So again, on the diffraction page, they have interference patterns. So clearly Wikipedia doesn't really understand that diffraction is supposed to be different than interference. Yeah, they're supposed to be different. The rest is simulation, 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 simulation. So now we have a real thing here. Now this is supposed to be the single slit experiment, right? So they used the most lame drawing possible, right? Which this you know, I can show you. Here's single slit diffraction. So they're using the lamest possible image to indicate that somehow there's, look, it's nothing. It's 4% of this. It's nothing. You can't even see it. It's, the diffraction's invisible. Blah, blah. No, it isn't. And so I'll show you a better page, right? But there's no water waves in this whole page. No actual image of an actual water wave going through an actual single slit and actually just creating normal waves. Instead, it's all manipulated waves. The gap is really wide and the frequency is too high. So obviously if you create a high frequency wave, it'll break down as soon as it hits the slits, if the slit is wide. But it won't happen in a normal condition. And clearly no one's doing the light experiment with a slit 5 times the width of the wavelength of the light, because guess what? You won't see anything at all. You'll see a little dot, period. You won't see any diffraction. So again, the two are dissimilar mathematically, fundamentally different mathematically. God, so irritating. Anyway, alright, so let's go to the Google image search, which gives you a little better pictures. This is single slit diffraction in various forms. So I'll show you the Lewin video of this. But clearly you can see all those little bars there, very clear. This image even more so, very different proportions here for whatever reason. Again, the math is supposed to be the same math. Well, clearly it's not. This image clearly doesn't even match this. I mean, clearly this isn't 8 times brighter than this. It just isn't. This is sort of I love this image in terms of being one of the better comparison images. So here's single slit diffraction at a very tight. This is the same width as one of the slits in the double slit is here. And you can see that this essentially superimposes over this. So the two slit experiment is essentially the single slit is superimposed on top of the pattern. I mean, that's a clear indication there anyway. But clearly these are quite obviously quite distinct dead places. Quite distinct. Diffraction minima, they're calling them. Obviously they're supposed to be interference minima, not diffraction minima. You know, but whatever. Let's see if anything. This is good because they show it widening. So with the slit open very wide, it's this. As you start getting narrower, it starts stretching it, stretching it, stretching it. So you can sort of see the lensing effect. That what you're really doing, in a sense, as you make the slit smaller, it's like bringing the screen in, which is the same thing as applying a lens essentially. So you start to make the lens more and more powerful, thicker and thicker and thicker. And that would also have the same effect of stretching everything bigger. And that'll be part of the point I'll make. So again, very different drawings of the mathematics. Huge, tiny, tiny. And then you'll find on the same page, this is single slit. Let's see if I find another image of it. Well, you can just see it in this image here. Clearly, this is bright, but it's not, 80 times brighter than this. So again, here's another one. Huge disproportions. When the experiment's actually done, it doesn't come out that way. Fact. Anyway, let's see where else to go. I mean, clearly at this width, those proportions are idiotic. I mean, clearly this is not 4% of that. Clearly this isn't 4% of that. Right here. Would you say this is 80 times brighter than that? And that's, well, 80 is about what this kind of a drawing is, comes to, not this one. See, this one's better. But that other one was just preposterous. So anyway, this is the science. It's very bad. So this is water waves, essentially. straight waves. There's no diffraction, and I mean there's no interference. There's no dead spots. And this fringe is a moving wave, not a static wave. So there's no spot that's dead all the time, which is what this represents. Dead spaces, dead spaces, dead spaces. The dead spaces are the whole definition of this phenomenon. That's a good picture of single slit. I mean, the center maxima is very bright, but as you widen, as you narrow the slit and widen the pattern, those proportions change dramatically. Alright, so anyway, so the point is that obviously this is there to be manipulated. So this is traditional water waves right here. Almost looks like my drawing, but you know, that's it. That's what water does. No interference bars created. Do that with light interference pattern. Alright. So yeah, that's probably enough for this. So let's go to, I guess we'll do the Lewin thing and little bit he does on it, which I've played before, but we'll do it again. Just to illustrate the point that this is single slit, and you can clearly see it. Clearly. Alright, now let me put this audio back on.
Of the bright spot is now entirely dictated by the divergence of my laser beam. The diffraction width is negligibly small because A is very large. But now what?
Well, the diffraction width is this, the width of these bars. He's saying it's negligible. It's quite obviously not negligible. It's quite obviously seen, as clearly these are brights and darks and brights and darks. So
now I'm going to tighten.
So this is with the width of the slit being equal to the total width of the double slit. So this is a single slit at a very wide width. That would be the total of the double slit. That's why it's similar to the double slit, because it's using the same width as the double slit, total width.
Make A smaller. I'm doing that now. I'm making it smaller and smaller. The diffraction which is still negligible. Making it smaller.
Right, you keep saying it's negligible, but obviously it's quite distinct, quite obvious. We see the dark bands quite clearly. It's not negligible. It's negligible compared to the central maxima, which is brighter. Clearly, and the reason it's brighter is because it's a single slit. There's nothing in the middle blocking the middle light. Obviously, the middle is going to be brighter.
I'm beginning to see the dark lines.
Oh, he's beginning to see them. You know, I saw them right from the beginning. I didn't need you to stretch it out for me to see them. But sure, now I see them too, but they were there before. But clearly, you can see in this image that the intensity of this band compared to these other bands is a lot more proportional. It doesn't look quite as horrendously 8 times brighter.
The diffraction which is taking over. Look at the center maximum, right there. It's getting wider. It's getting wider.
Everything's getting wider. Everything. Every single piece of it's getting wider, as if I just move the screen closer and closer.
And I make the slit narrower. It's getting wider. It's getting wider. And look how beautiful you see these destructive interferences, where light plus light gives darkness.
Right, okay.
Wider.
Where is that
Wider.
in a water wave? This, again, is a single slit. Light plus light gives darkness. It's a single slit. Light plus light gets darkness. Now, you can only do that with the Huygens gimmick, where you end up creating 2 photons. There's no 2 photons. There's 1 photon. It goes through and it goes somewhere. It doesn't interfere with itself. It can't, because there's no slit creating the second photon. I mean, people really ought to get that that's a real problem with the logic of what they're arguing. It's a problem with the logic of what they're arguing. If you can't concede that, you're just being dishonest.
So right now it is at least 10 times wider than it was before. Now it is 20 times wider. And it gets very faint. Of course it gets very faint.
Yes, because now there's less light going through because the slit's very small. Yes. Okay, so I guess that's enough, right? You don't need to dissolve it any further. So there is a question about the central maxima and its size, and I haven't figured out that one exactly yet. I mean, it's quite obviously made of, I think, two maximas, and the center gets wiped out by the actual photons that don't get interfered with, and they fill in the middle. That would be my argument, but it doesn't really matter. It's not. It's something still needs to be answered. But I'll just make this argument for the purpose of this explanation, to qualify what I've said and to say it a little better, hopefully, to describe it a little better. Okay, so what we're really seeing is kind of like the balloon argument. If I take a balloon and I blow the balloon up, everything gets bigger, right? Everything on the surface of the balloon gets bigger, 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 as I'm expanding the surface of the balloon. And essentially that's what's happening. As you make the slit smaller, something's ballooning the image, some mechanism. Now, I've argued that there's electrons between all of these. All matter has electrons surrounding it. And when the slits are comfortably distant, those electrons are they form whatever their native condition is, their relaxed condition, let's call it. So they're filling the void between these two things because one ends up being positively charged and one ends up being negatively charged as they become associated with each other. That's the tendency, because the electrons are always going to search for they want to get as far away from the other electrons as possible. And they're always going to be influenced by the surrounding field and what exactly is the softest place in the field to go to. So the charge tends to move to whatever location is closest to a place that has less electrons. So I mean, it's a little complicated because clearly you could have a lot of positive charge in one location, let's say. And then that location has some electrons around it that don't crash into it, of course. Now, you could have a net more positive than negative here, but the problem is the negative exists as a wall, a barrier. So the electron is just going to, say a new electron coming into this circumstance, is just going to see these electrons. I mean, it's going to feel this, but I'm saying it's going to see the electrons, and the electrons is what's going to say, no, I can't go there. So even though it wants to go there, it can't go there. So it's going to find some position neutral to the electron and still be affected by the bigger field, which would be this bigger positive field. So it wants to stay in the bigger positive field, but as far away from this as possible. So it'll end up on what are called field lines, which are sort of neutral positions where there's a tenuous balance between the repulsive force between the electrons and the attractive force between the protons and the electron. So it's being pulled by one piece and pushed by the other piece, but the push pieces are on the outside, which gives them advantage, so to speak. Alright, so in the two slit, and when you have a wide opening, what's going to happen is the electrons will be in their most comfortable position, let's call it. Let's see how best to say it. They're you know, it's I just have to be careful. I'm looking. I have this stuff written down, but I mean, it just get a little complicated to read and then say it, and then make sure I don't say it backwards. Okay. All right. So, if you thought of this as a lens, so just think if two objects come together. So if they're far enough apart, you're just going to see the laser light as a plain laser light, because it won't be any. There won't be anything affecting. There won't be anything in here in the way, in the sense there won't be any electrons out of position. So whatever hits them gets emitted exactly the way it was in the same direction, because they're in their standard position. Now, if I start pushing those two things together, this matter with electrons, so now I've pushed them together, what I'm essentially going to be doing is pushing those electrons tighter than they want to be. And the excess, the pressure, is going to be in this direction. They don't have anywhere else to go. So they're going to tend to bulge out this way in terms of the field lines. So if you thought of it as field lines, they both have neutral field lines. You could sort of understand that as the field lines get compressed, they're going to push this way. They're going to tend to push this way. And as I go tighter and tighter, I'm going to bulge these ends more and more. So that's essentially the lens. And you can sort of see that what's going to happen is as this bulges more, so let's just draw that bigger. So here's a lens, and here's a lens bulged more. You can sort of see that the angle, as it bulges, this angle, so you just think of these has to be perpendicular. So the photon that interacts with an electron on this field line will always leave perpendicular to the line. So there is, if you take it as a little straight segments here, if you cut them all into straight segments, there's a perpendicular angle, and they always leave on the perpendicular, like fields created around a magnet. It's always on the perpendicular. So obviously the perpendicular, as this bulges, the perpendicular when it's lightly bulged is just, this much, this angle. Giving you a 90 degree doesn't help you much, but it's this angle versus this angle. This is obviously 90 degrees to straight. This is obviously something like 45 degrees to straight. So obviously the end is, the angle will be doubled of the exiting photon that affects an electron on this field line. And so that would explain this bubbling effect, this idea. It's just like a lens. The lens is, the more you bulge it, the higher the angles get, the sharper the angles get. Now the other fact is that the lens is thickest here in the middle. So the smaller angle, as you bulge it more and more, there's more electrons you're likely to hit here. There's thicker. And there's a lot thinner here in terms of the amount of electrons. So the highest angle will be the weakest probability, and the strongest is the most blacked out. So in effect, the light that goes straight through, will likely be light that is only going to go through, if you look at it as a slit. Wow, that was a great drawing. The light that ends up going straight through is going to end up being this light close to the slit, which is counterintuitive. And the light that's going to get refracted or bent is likely to be the stuff going through the middle. So as I tighten the slit, the opposite thing starts to happen, where the light in the middle is the light most likely to get refracted, although it won't be refracted as high an angle as the light over here when it does get reflected. So the more electrons, the more likely, the higher the density of electrons, the more likely you are to hit one, and so the more likely you are to get refracted. So that's what's happening here. As the slit gets really narrow, the lens bulges. Lots of light, not lots, a few photons are going at very high angles way over here, but it's very few, so you don't see them. They're there, but we don't see them in this image. But most that get refracted are going to go right through the middle and get only refracted like 7 degrees or 6 degrees or 5 degrees. They're not going to get, and the amount of refraction is dictated by this parabola. I don't think it has to be a parabola. Obviously, it has to be a it has to be a curve, but it won't be necessarily a parabola. And you could break it down to be precise, because it does all leave perpendicular. You could understand it as a hexagon or an octagon or some other shape, that these are facets, that the field line is essentially made of facets, and that's why it all leaves at that angle from that one facet. Alright, but anyway, that it's not terribly important. The point is that you can understand that there's a proportional relationship to this angular change. The amount of change has this, it's on a curve, and I wouldn't say it's a parabola, it's a, whatever the term is for a bent line, a curve. It's a curve, but it's a curve that changes depending on how tight the slit is. It linearly changes. That does not necessarily in a relationship to pi for a circle. Well, pi would still apply even if it isn't an ellipse. So, but it doesn't really matter. It's not I'm not saying it doesn't matter. It would be important to be clear on that, but it's not critically important to this as a theory or of an explanation for how lensing is taking place, and that the lensing isn't a substance lens, it's a lens of electrons. And electrons are the fundamental mechanism of what we see in material lenses. So when we see a material glass lens, the thing that's really doing the lensing in this glass lens is probably electrons. And it's just the matrix of the matter that's holding the electrons in the right configuration to cause the lensing. And so the only argument being made here is there's also electrons that are outside the material structure, and those electrons are just as capable of refracting light if in positions that'll cause them to do so. So they're still part of the matter. I don't want to confuse that. They're the surface of the, they're still associated with the protons in this matter. They still want to get to the protons. They're just being blocked by a shield of electrons. So they're just stacking on top of the shield of electrons, and that's commonly called charge. Alright. What else do I have to say? So you're automatically going to have the charge will automatically take care of itself, in the sense that even in the two-slit experiment you'll end up with, say if it's minus here, it'll be plus here, it'll be minus here, it'll be plus here. So you're always going to end up with a charge field here and a charge field here. And it really doesn't matter whether you invert those or not, you're going to end up with either the positive here and the negatives here, or the, or vice versa. It doesn't really matter. You still end up with the same amount of each charge. So if there's a difference in the two sides, that will be reflected in the results. There's no way to, it'll always end up balancing, and anyway the lens will end up balanced. Alright, so is there anything else I wanted to point out about that? It's just, I just write little notes, and I should do better than that. Leave perpendicular to the field. Okay, so that's the idea of the thickening lens. They leave perpendicular to the surface of the lens being created out of the field. And again, these field lines, you can do this with, I probably should have to look up some EMF field configurations and some magnetic field configurations, but it is true that when you pile two fields next to each other, especially two positive, a positive against a positive, for example, you'll definitely get a compression of the field lines, and they'll end up bulging, in the way they'll be configured because of the electrons not liking each other. So that's essentially what I'm talking about here. It's just a bulging which is causing the electrons to be in a new position, and in the new position they're oriented where when they absorb a photon and they're going to release a new photon, they'll release it in their spinning orientation, the orientation that they're in. And their orientation is going to be dictated by where they are on that field line, perpendicular to the field line. It'll be their orientation. They line up like wheels spinning. They all spin on that field line. So as so at the top of the field line they're spinning this way. At the bottom of the field line they're spinning this way. 90-degree difference. And so it's everything in between. And the point is that there isn't everything in between, because this lens is describing the bulge in the field lines here. So the lens is being created by field lines that are really moving, well, that are really moving this way. But it has the same effect in the end, in the sense that the only part that matters is the part where the most exterior part is the last electron dictates where the photon goes, not the first electron. You know, the last one it hits. Yeah. So technically a photon could be diffracted here 7 degrees, and then it would hit here and then end up leaving parallel here at a 22 degrees or something. So, but it's always going to be I guess that would account for why there's some noise in many of these patterns, is that I don't even know if I want to go there. Let's just stay with the facets. So they're on facets, and the facets are deciding these locations. So they'll only leave on those facets. So there's only, I just didn't want to draw it like the field lines. I don't want to draw the field lines inaccurately, but they have to sort of be understood as being going in between the two slits in this kind of pattern. But the real important part is this end part, and this is where the shape of the lens is being made. So I guess that's what I wanted to try to illustrate, is they had to hit an electron, they have to be on this line, but it'll be this curve is where they're going to leave. So it's this angle they're going to leave at, but they have to hit an electron, they have to be on the field. They have to hit the field line. You have to hit the line that has the electrons in it, that the electrons are lined up on. And remember, the electrons don't like each other, so they're going to tend to proportionately distance from each other. They're all going to be a proportional distance from each other. They're going to attempt to be in a proportional distance from each other. Alright, that's probably enough to get the theme. So, I'm going to argue that in this electromagnetic spectrum can be affected by lenses made out of electrons. The electrons that are associated with matter. Now, it can probably be free electrons also can do this, but free electrons in the universe just aren't that common. Electrons stick to things. So electrons are usually going to be stuck to a surface. So you're not going to hit too many free electrons in day-to-day living, because they're going to tend to be attracted to something with a proton in it eventually. Alright, so that's probably enough for clarification, I think. Yeah, so the more electrons in the center, means the more light is diffracted at the smaller angle, and that's why you have this big pattern in the middle. And the light that goes straight through, that also makes this brighter, is coming through the entire slit. Like I said, the light most likely to get through as the lens bulges is the light on the outside. Whereas when the lens was flat, the light on the inside was more likely to go straight through. As the lens bulges, the light on the outside is more likely to. So it reverses as the slit gets narrower. And I think that's why this brightness proportion changes. Essentially, all the light that doesn't get refracted at a high angle because it doesn't hit an electron in that location ends up here. And that accounts for the brightness difference. Okay. Part of the brightness difference. The other part of it is that these field lines, as they compress, if the two things push into each other, it's likely, okay, as these two fields are sitting here compressing into each other, they're likely getting more compressed at the ends. So there's a higher density not only in this part of the lens, is not only higher density in terms of the length of available electrons, it's also these field lines are closer together out here than they are in here. So the compression starts at the intersection point and moves in. So these become compressed first. And as the slit gets closer and closer, that compression moves deeper and deeper. Okay, so that's another point to make. So eventually I'll work on this, but I don't want to take too much time just working on one experiment and explaining it. But because I think the overall bigger picture theory is more important. And clearly, even if I dispute particle duality, there's going to be plenty of people who are just going to pretend some other experiment indicates something. So it'll just be hop from experiment to explain how the interpretation, the photon goes through both slits, is incorrect. The experiment is correct. The interpretation is incorrect. Okay. That's probably the point I'm trying to make, is that how experiments are being interpreted is what's being argued, not the experiment itself. Except those experiments that they're making up, the ones that never happened, are the ones that only happen if you manipulate the conditions of the experiment to create results you're arguing are the truth. And again, as the different variations, depending on the slit width, the variation, see this looks like nothing here, but it's in the double slit, these lumps are much larger. So again, it's this is where the two patterns overlap. Single slit envelope, they call it here. But the single slit envelope is a lot more. There's a lot more to it than this. This is deceptive in that it makes it look like the envelope. This is almost invisible, and it's not anywhere close to almost invisible. So anyway, all right, enough. I think. So, this is the difference. The interference pattern is created by the intersection of two waves. And in single slit, there's no interference pattern because there's not two waves to interfere with each other. And to sit there and use some word like diffraction as if in the single slit with light, it's not diffraction. It's the same pattern. It's the same on-off, on-off, on-off. There's no on-off here. And with light there is.